On this project, a centrifugal pump was designed by using computational fluid dynamics, or CFD for short. Centrifugal pumps are highly used on low viscosity fluids to transport them, such as in the transport of water, on the industry, and sometimes to pump crude oil. And we used a CFD simulation in order to model, predict, and analyze the fluid inside the pump. On this design, we made several assumptions. The first one is the steady state, so that the intake and outtake of fluid was constant. These non slip conditions, so that there was no relative motion between the fluid and the impeller. Non compressible fluid, so that the density remains constant. Isothermal conditions, so that the dynamic viscosity remains constant, and we calculated the Reynolds number to determine the regime. After calculating it, both fluids uh, proved to be highly turbulent, so we chose the K epsilon turbulent model to model them for a faster time in computations with a fairly accurate prediction of the results.
These are some of the important measures of the pump. We have manufacture data, geometry constraints, operation constraints, velocity triangles, and in the table 4 we have other important calculations.
Here are the detailed dimensions of the impeller. All measurements are in millimeters. The outer diameter is 308 millimeters, and a detailed view of section L is shown on the right, where the blade width and impeller eye diameter can be seen more clearly. A cross-sectional view is also shown. The cross-sectional view shows the height measurements of impeller, as well as the inner diameter of 108.59 millimeters. Other useful measurements for impeller construction are also shown in detail. On the right, there is a 3D view that shows the shape of the piece. For the volute, there is a top view where you can see the suction nozzle diameter of 80 millimeters, as well as other important measurements, and a cross-sectional view where you can see inside the volute. Here, you can see in detail the discharge nozzle diameter of 65 millimeters, as well as the height of the volute, and a 3D view that shows the shape of the piece. In these figures, you can see the assembly from a top view, where you can see the volute with the impeller inside. There is also a 3D view on the right side that shows it better. Here is a cross-sectional view of the assembly, where you can see the impeller inside of the volute, and on the right you can appreciate the side clearance with a measurement of 2 millimeters. There are three criteria for deciding which mesh to use: the MSE of efficiency, the MSE of head, and computation time. This table shows these parameters for each mesh: thick, reference, and fine. In these graphs, you can see the total head and water head MSE for each mesh. And here you can appreciate the efficiency and water efficiency MSE for all three meshes. After analyzing all three meshes, efficiency was prioritized, and we chose to use the reference mesh because it has the lowest error in efficiency. Here you can observe the chosen mesh, which was the reference mesh, in K locations of the pump's internal volume.
The graph below represents the flow rate versus pump efficiency curve. To create these characteristic curves for simulations were conducted at significant flow rates specified by the manufacturer. Subsequently, we determined the maximum point on the curve using a second-degree polynomial regression. The flow rate at the resulting BEP exceeded the manufacturer's free delivery flow rate, a phenomenon that is clear in the graph. As can be observed in the table, the best efficiency point for water is significantly higher than the BEP for oil, approaching the manufacturer's specification. This phenomenon is explained by the influence of the fluid viscosity with which the pump operates. As the viscosity of the fluid increases, the resistance to flow also increases, resulting in a greater demand for energy to transport the fluid through pump and pipes. Additionally, it is important to note that designing a pump for a specific type of fluid with particular characteristics is not equivalent to operating it with a different substance. This situation can provide a plausible explanation for why the best efficiency point is higher for water compared to oil. The following graph illustrates the pump head against flow rate. As observed, our pump exhibits an abnormal behavior at low flow rates, suggesting that the pump may be unstable with this range and the operational restrictions may be necessary. Additionally, the table reveals that, similar to efficiency, the head is higher for water compared to oil. This indicates that the pump generates greater pressure when pumping water, which can also be attributed to the physical properties of the fluids. Furthermore, as indicated by the graph, it is evident that water can handle a higher volumetric flow rate with a lower head, a characteristic that can be particularly advantageous in various applications, such as cooling systems. Lastly, we have the graph of hydraulic power against flow rate. An unexpected behavior is evident as the pump transfers more energy for water compared to oil to achieve a specific head. In summary, we can infer that the manufacturers likely designed the pump with a preferential focus on water usages, as the obtained values closely resemble the specifications provided by the manufacturer.
The graph on the left shows that all data points are within the 10% deviation region, which is the base error value that was estimated from the RMS, which was 8.55%. This can mean a good representation of reality. Likewise, the efficiency values have a deviation less than or equal to 25%, which was the percentage of error estimated from RMS. It can be seen how at a flow of zero, the minimum speed is needed at the inlet, but it is the flow that needs the highest rotation speed near the blades, mainly in the case of water. This could be due to the low flow rate, thus forcing the impeller to exert greater speed. On the other hand, as the flow increases, the inlet velocity increases slightly. In this case, the speed in the impeller, mainly close to the blades, begin to decrease. This could be due to the increases in flow, thus making the impeller need less speed so that the flow at the end is constant. There are slight differences between water and mineral oil in the part of the diffuser, where water always reflects greater speed, which could be due to the low viscosity of this fluid and the ease of transport.
In the velocity profile SVEP, a notable change can be primarily observed in the impeller. However, the inlet and outlet velocities remain quite similar for both fluids. The animation revealed that water exhibits higher velocity, especially within the impeller. This is because water is less viscous but more dense, which results in a large volume occupancy. Consequently, there is a less resistance, making it easier to increase the impeller's speed. While cavitation is an undesirable process in a pump, it is not critical if it occurs at the center of the pump, at the origin of the blades. For lower rates, such as 0 and 90 cubic meters per hour, cavitation is minimal for both fluids. There is noticeable increase in water cavitation primarily due to its boiling point. Similarly, it can be observed that for the subsequent flow rates, cavitation remains constant. This is because at these flow rates, the pumps are already operating within their optimal performance range, and any acceptable increase in cavitation it is not generated. For the flow rate at the web, there is a considerable increase in water cavitation. This may be attributed to water's lower boiling point, leading to cavitation occurring near to the blade origin and within the impeller's eye. This could be a result of improved pump efficiency and possibly a temperature increase in those sections.
It can be seen that the Wallway Plus is quite consistent across the different flow rates for both mineral oil and water, and both are small values which is appropriate and expected. Likewise, it can be observed that in the case of mineral oil, it has much smaller values, which shows that the wall is influenced by the viscosity of the substance. In the same way, by having values so close to zero, we can intuit that the surface is practically smooth in the case of mineral oil, while in the case of water, the roughness can begin to be considerable in the simulation. It is evident that pump performance and efficiency is directly influenced by viscosity. At higher viscosity, the pump efficiency decreases. It is important to mention that pumps must be specifically designed for the flow to be pumped. For this, it is crucial to take into account specific operating restrictions and criteria for each fluid in order to optimize pump efficiency. Likewise, it is important to mention that at low flows, the pump is unstable. For this reason, it is necessary to define an optimal operating range.